Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everybody. It's my pleasure to introduce Abhinav Pathak. He started as an intern in MSR in 2009. And during that time, he worked on some problem about how to split the computation job from mobile system to the cloud. And that motivated his follow-up work about using some models to predict energy usage on smartphones. And then he went on to work on a bunch of stuff about how to debug energy consumption on smartphone, how to profile energy consumption on smartphones, and that generated a lot of press coverage recently in BBC News, MIT Technology Reviews, etc. And he will cover these topics during today's talk. Okay.
Thank you, Ming. Thanks for the introduction. Hello, everyone. I'm Abhinav Pathak. I come from Purdue University, and those who don't know where Purdue is, it's located right in the middle of nowhere, surrounded by miles and miles of cornfields, flatlands, wherever you see. So today I'll be talking about some of the work that goes as my PhD thesis, and which is energy debugging in smartphones. This is already 2012, and it is very safe to call this is the era of smartphones. Very old news, smartphones are selling more than PCs. We are seeing this from last quarter of 2010, 2011, 2012, the trend continues and it's increasing. But what we are seeing is people really use their phones. They depend on their phones. And it's predicted that the number of people who will access internet from mobile devices, from smartphones, will exceed the number of people who access internet from PCs. This talk is about one of the most critical problems in smartphones, which is of energy consumption. Why is this problem there? Energy is a very, very scarce or sacred resource on smartphones. Smartphones comes with a limited battery life. And if you look at the last 15 years of research in battery energy density has only doubled. Whereas you see modern day smartphones, they're getting faster CPUs, multiple cores, 3G, 4G, retina displays, GPS, cameras, multiple cameras. And basically, there's a problem between producer of energy and the consumer of energies. Since energy is getting a very, very critical problem, what we have started observing in smartphones is a new kind of bugs, which we call as energy bugs. What is this phenomenon? Whenever an energy bug strikes you, you get a single symptom. From that point onwards, your phone starts draining battery at a very, very high rate in case of the most notorious energy bugs. You don't see an application crash. You don't see a blue screen of death, like an OS crash or something. Everything works fine. Your Facebook runs, your Gmail runs, your client, everything, all the applications are running. But then you just observe that the phone is draining battery at a very high rate. And normally this is very frustrating. People think the common perception is some app has gone rogue. So let's try to open a task manager, kill some applications. In some cases it helps, in some cases it doesn't. In most of the cases it only makes the problem worse. Irrespective of that fact, it is very, very frustrating. And we start down this line. What is this new thing that we are observing? What are these energy bugs? Where do they come from? What are we dealing with this here? We never observed this in PCs and laptops. So we did a lot of data collection just to understand what are these things. We went to mobile internet forums. These are places where people post what problems they are facing in their phones. We went to 4 really popular mobile forums. We collected about 1 million posts of these users. We did some data mining on these posts, got out what are energy, posts related to energy drain or severe energy drain. We did some clustering on this. We had 39,000 posts related to energy. We did some clustering. And once we got 1,000 clusters, I sat down and read all of them, basically trying to build a taxonomy of why is this problem happening. We also went to mobile code repositories like Android, Memo, open source repositories, where we found we were looking for the patches that developers put to fix energy problems so that we get some insight, why are these problems coming in applications? And with all this information and some information we obtained from the tool we built, which I'm going to talk today, the energy profiler, we built a energy bug taxonomy to see where the problem comes in, where the problem comes from. Let's see, where does this energy bugs come from? Well, that's one of the most obvious places to look for. Something wrong happens in application. And now your phone starts draining energy at a very, very high rate. If you use Android phone, you make a phone call, depending on the version and the hardware, let's say, irrespective of how long you talk, after you hang up the phone, put the phone in your pocket, your phone is going to drain battery. Your battery may go off in 12 hours, even though you're not using the phone. It's just in your pocket. The problem can come from framework, like Android, Memo. Something is wrong there. Something is wrong programmed, or things are not working the way you want it to. Problem can come from OS. And this is very popular in news. Whenever a new version of iPhone or iOS comes out, a lot of people scream that new version of iPhone has a lot of energy problems. For the first time, after iPhone 4S comes out, Apple acknowledged that iOS had a problem, had an energy bug. They fixed it. Even that version had a problem. They fixed another one. Even that had a problem. And finally, in November end, they were able to make the problem go. We found that the problem can come from device drivers. Something is wrong in device drivers. Things are not working the way you expected it to be. Or from the hardware, people are complaining that even your hardware could be a source of problem. Something is wrong with the battery. Something is wrong with your SIM card. Something is wrong with your SD card. And the final thing is these kind of energy bugs come from network operators. Something is wrong in your network, and your applications now start draining a huge amount of energy. So out of these huge number of posts, 39,000 posts, we did this classification of which categories these posts fall into, just to give some rough numbers. Hardware was 23%, software was 35%, external was 12%, 30% of people didn't realize where the problem is coming from. In hardware, the problem can come from external hardware or internal hardware. You have a dock, let's say, and now the pins on the dock are short-circuited. So whenever you place your phone on it, your phone drains battery. Or the problem comes from your charger. Your charger is faulty. It's not just charging your phone properly. It could come from internal hardware, which could be your battery has gone old, or the interface between the battery and the operating system is not correct. So it's not able to read how much battery is left off. Your SD card has a problem. Some corrupt sectors in SD card, and now your applications are going in a spin. Your SIM card has a problem. It's probably an old generation SIM card, or something wrong happened with the SIM card. Any application that accesses contacts on your SIM card is going to drain a huge amount of battery. It just hangs there and tries again and again. The problem could come from external place. For example, an external service crashed. A mail server crashed, and now your mobile is trying every 5 minutes to authenticate to the server. Goes on for hours and hours and hours, and now you're draining battery without doing anything good. Problem comes from network signal strength. You're not in a good signal strength area. And the recent numbers that we have is, if you move to a bad signal strength area, the energy consumed to do a certain work can increase by 10 times. Or it could come from wireless handovers. You're moving on a road. You're shuffling between 3G to 2G or edge, and your phone is in your pocket, nothing is going on, and now battery is gone completely. Yeah?
Why are you calling signal strength a bug?
It follows the symptoms. Anything that follows the symptom that there is an unexpected energy drain. We term it as an energy bug. You can call it an optimization problem, or you can...
In that case, using the phone is a bug.
Sorry?
Using the phone is a bug.
Unexpected, again. It is, you use the phone, it is still slightly expected that the energy will go down.
So everything's a bug then.
Okay. Most of the problems are, let's say, optimization problems. You're trying to optimize energy. But some of the cases we are saying you're not even using your phone, it's in your pocket. Application is one of the main source of energy bugs, and we found that there are 3 kinds of bugs coming out from application, which we call no-sleep bug. I'll deal with this in detail in this talk. Energy loopers. Something bad happens, and now your phone is looping in a loop. for no good reason, draining a lot of battery. Or energy immortals. That is, something bad happened in your application. It reached a state where it is draining a huge amount of energy. Irrespective whether you kill it and restart it, it will still spawn from the same buggy state. Even if you reboot the phone and restart the application, it will spawn from the same buggy state. So basically meaning, if the app enters into that state, you cannot use it ever again.
So how much of it is OS specific? Is it just an Android issue, or have you validated this on Windows Phone or iPhone as well?
So again, the study comes from which the posts, let's say, and which phones are popular. You'll expect more posts in that side of things. Here we are looking morely at Android, iPhone, a little bit of Memo side of things. But then things are pretty common. It's across different phones.
Even for the iPhone?
Even for the iPhone, yeah. Mostly bugs are classified further into 3 categories, and I'll talk about it in detail in this talk. This talk is focusing on application energy bugs. So let's say you have an application. It's very popular. A lot of people are using it. But suddenly now people are started complaining that your app has a huge amount of battery drain and it's really hurting your business. You want to debug this problem. Now what's the first question you want to ask when you want to start debugging this energy problem? The first question is, okay, where is energy spent inside my application? Only if I have this information, I can maybe start looking at how do I fix it. And when we started this research in 2009, 2010, we found out that there's hardly any tool available which answers this kind of question. And this thesis builds eProf, or an energy profiler, which answers this question: where is energy spent inside your application? Which process, which thread, which routine in your application is taking how much energy? Why is it taking that much amount of energy? What can you do to fix it up? And things like that. This is built on a fine-grained power model, which is capable of predicting energy consumption of the phone at a very accurately. However, this is still semi-automatic approaches to debug energies. You have a profiler, you need a developer, run it, get the data, fix the bugs, again and again, do it in a loop. We can still build things in an automated manner, targeting each one of these application energy bugs in isolation. For example, we have bugs and mostly bugs, different categories, energy loopers, energy models. We can get a lot of ideas from different areas of computer science, and we'll show in this talk, one particular example where you use a compiler's approach to solve no-sleep bugs, one of the most notorious energy bugs in application, automatically without the use of a developer. So let's see on the first part, where is energy spent inside my application? And I want to answer this question. It's very simple. I need to do 3 things. First thing is, I need to track power activities on the phone. Second thing, I need to track application activities on the phone. And the third thing is I need to match these 2 things. Which application is taking how much energy? Sounds pretty simple. Let's see. How do I track power activities on the phone? Simple, layman's solution. Use a power monitor. Buy a pretty expensive instrument. Perform some surgery on the phone. And now this equipment can get you very accurate energy readings of the phone. But the problem is, this equipment only gives the entire phone energy consumption. It doesn't give you which application, which thread in an application, which routine in a thread, and so on. This kinds of information. So second thing is we need to use a power model, build a software power model. And when we started looking back in 2009, 2010, about what are the power models available in servers, desktops, PCs, laptops, mobile phones at that time, we found a lot of power models, they use something called, a utilization-based models. They say, we have 2 phases, one training phase, one prediction phase. In training phase, we'll actually measure the power consumption. We'll measure the triggers around which we want to build the model. We'll do some mathematics. We'll get a model out. And in the prediction phase, we'll use those triggers again. We'll use the model, and we'll generate the output of power consumption. All the research on servers, laptops, PCs, on smartphones, most of them fall into a category of what we call as utilization-based models. And they say your hardware is using energy only when you're actively utilizing it. They come up with a very simple equation. Model energy is equal to, in last 1 second, how much packets I have sent over network, how much packets I have received over network. multiply by some constant. In last 1 second, how much CPU I have utilized, multiply by some constant. Similarly for disks, similarly for every other component, write a simple linear regression equation and you get the power. When we picked this model up and we applied it to smartphones, we found that these models fail terribly. Why does this model fail? The first, yet very, very intuitive assumption that this model makes is only active utilization implies energy consumption is not true on phones. Your phone can be draining energy, a hardware component of the phone can be draining energy even though nobody is actively using that particular hardware. I'll show examples of this. The second assumption here made is an implicit assumption that energy consumption is linear to the amount of work, and that is why you can multiply how much utilization of network into some constant. Basically, they're saying if I send 10 packets, I consume X amount of energy. Sending 20 packets implies 2x amount of energy. That's not true as well. Sending 20 packets can consume 3x, 5x, or in a corner case, half x amount of energy. I have a question.
It's in like low power radios. This model certainly doesn't exist. I mean, there's a model explicitly, for example, idle listening power, transmit power, receive power, and sleep power.
Right.
So it's a much. It's certainly not this model that if you're not transmitting or using it, it's not using any energy.
So we observed that a few people have started at that time looking at individual hardware component and they're saying, power model is very, very complicated here. The simple things, this-like things don't work. For example, in network, especially 3G, people started seeing this kind of results and they're saying, we need tail, we need this, and things like that. I'll cover in the next slide. But we observed that this is true not only for radio, not only for NIC, for most of the components in smartphones. I'll come to the examples here. Stefan.
No question.
Okay. One of the important property of a power model that we started from is we need to get the power model to tell which process, which thread, which function is consuming how much energy, but it's very hard to obtain these counters that goes into this particular equation at these levels. So it's very hard to predict energy at these low levels.
Assumption that energy consumed is a linear combination of its components.
I'm skipping that.
Should not hold at all. It seems it should not hold.
Right, that's true as well. I'm skipping up from this slide, but that is true that you can't add energy individually. Some components interact in terms of energy consumption. I'm skipping from this talk, but we can talk about it. First example, only active utilization implies power consumption is wrong. We took a HTC touch phone running Windows Mobile 6.5. We run a simple benchmark. We connected it to power monitor. X-axis plots the timeline in seconds. Y-axis plots the current consumed by the entire phone in milliamps, which is just same as power, multiplied by 3.7 times the voltage of the battery. Nothing else is running on the phone. We run a simple benchmark, which opens a file, reads from the file. Opens the file, sleep for some time, read from the file. What we observe, the first thing is, the moment you do a file open, there's a power state transfer, a trigger. The file open takes a few milliseconds to get completed, but then it consumes a huge amount of power. When you do the file read, again, you see the same things. One thing is, in the traditional power models, file open is not considered an active utilization of hardware. It's only read and write calls. But we observe that calls like file open, file remove, file close, file create, all of them are capable of doing a power state change. Second example, took a HTC Titan 2 phone, Windows Mobile 6.5, send some packets over the network. Even after you're done sending, this is on Wi-Fi, you see a tail for 2 seconds. No packets are being transferred in that particular time. Still, the hardware is consuming some power there.
So again, a lot of this will be OS specific, right? That is how long the state, especially the first one, the SD card, that is dependent on the driver. That's fixed in later versions. It's 6.5 at this point.
So it comes from the driver. We don't know if it is a bug or it's a feature. And
it's part of the OS, so
right, it's part of the device driver, as we can see, and device drivers try to manipulate the power of the hardware component, and that's what we'll try to guess later on. In some cases, it is needed. In network case, for example, it is needed because you're expecting more communication, and that is why you're staying in a high power state. But irrespective of that fact, your utilization-based models cannot capture these kinds of things. And tail phenomena is very common in 3G. We have observed it in 3G, in SD card, in Wi-Fi, in GPS, across smartphone hardware, across smartphone OSes. This phenomena is fairly common. Second, energy scales linearly with the amount of work. One simple experiment, took HTC Titan 2 phones, Windows Mobile 6.5, sent packets at the rate of less than 50 packets per second. Second experiment sent packets at the rate of more than 50 packets per second. This is how the power profile looks like. X-axis is timeline, y-axis is current. When you're sending packets at a rate less than 50 packets per second, you see 100 to 125 milliamps power spike. Increase the rate, the power consumed is triple. If you actually go ahead and consume the energy in the graph, the area under the graph, the energy is not linear right there. What have we learned so far? So far we have learned that there is a notion of power states. You do something, something triggers, and you go to a high power. You do something, it comes back to low power. What we assume is device drivers is doing these kinds of low-level power manipulation behavior. Stephen.
I'm a little confused by your previous slide because you doubled the rate. So the you somehow changed. You said if I send 20, when you talked about the slide originally, I said if I send 10 packets, I consume this much. If I send 20 packets, I consume double. And now here, what you've done, you doubled the rate. You didn't double the number of packets.
I didn't double the rate. You choose 49 packets per second and 51 packets per second. Irrespective, you're sending 10.
Not double, but you're manipulating the rate, not
the rate of packets sent. Yeah. So there is something, an intuition that there is a workload-based characterization here, power characterization, and that's what we see here. That the device drivers.
That 50 is the pivotal point.
A huge amount of experimentation, but we'll try to capture this in the power model. The thing is, device drivers are doing something intelligent down there, and the idea here is we want to reverse engineer what is the device drivers doing there. What are the device drivers doing there? The problem is device drivers are source closed. They don't leave companies like HTC, Samsung, Apple, and you need to do basically a black box reverse engineering of the power states inside the device drivers. Okay, state-of-art models don't work. So we went back to the scratch board. We said, okay, who consumes power in smartphone? Very simple, hardware consumes the power. There's nobody else who's draining battery in the smartphone. Who drives the hardware? Applications drives the hardware. How does the application drive the hardware? There's a very, very nice interface called system calls through which most of the applications are able to access hardware. And the idea is if we can capture the system calls effectively and we try to build a power model around system calls, maybe we can do a better job in terms of accuracy. And the advantages are very simple. We capture everything that utilization-based models see. Just look at the parameters of the system call. We capture power behavior of those system calls which need not imply active utilization, like file open, file create, file delete, file close. And the most beautiful part of this approach is system calls has a very, very nice property. They can be traced back to where they are coming from. Which process, which thread, which routine is doing the system call. So let's see. The challenge here is we are trying to learn the device driver power manipulation, and we are looking at only two things, the timeout and workload based. So how do we reverse engineer this? First thing is we use a finite state machine representation. We move away from linear regression equations. There are nodes in the power model. The nodes could be a base state where nothing is happening in the device, a productive state where the device is actually doing some work, and a tail state where it's waiting maybe for further communication or waiting for further activity. The edges from one node to other nodes are basically transition rules. They could be system call driven, start of a system call, stop of a system call, or they could be device driver intelligence, and we are looking at two of them, timeout and workload based, like 50 packets per second.
So the base state itself would be in different power levels, right? Think of DBFS for CPU. So is that itself different states, and how those transitions happen?
So base state for CPU would be nothing is going on. But
so the production state would be different states?
There could be multiple production states. There could be multiple tail states for a hardware. But CPU, we are handling it slightly differently. We are noting down the frequency. We're changing the value of the power.
It's for everything, right? Even for the network based on transmit power control, you will have different nodes.
Right. That is there in the model, based on signal strength, but based on the rate you're sending, you need to go to a different power state. I'll show that in a slide. The approach is pretty simple. It's a black box reverse engineering. We don't know what is the device driver doing. We don't have the source code. We call it a systematic brute force approach. We're going to try everything possible. What we'll do, all the system calls that are going to a particular hardware, we'll try to build a finite state machine for each of these system calls. And once we have the finite state machines for all the system calls to a hardware, we'll try to merge the finite state machines of different system calls going to the same hardware. This requires domain knowledge. You need to know how SD card works. You need to know how GPS works, what are the calls affecting it, and so on. Chitu.
So one obvious assumption here, I guess, implicit one that you're making here is that system call behavior is independent of what is preceded it, right? It's discrete event, right? Otherwise, you can't model a single system call on its own.
Not really. We'll try to combine things as well. The behavior.
How will it fit into your state?
Because from every state, we'll try to generate different system calls. Again, brute force approach, trying everything possible. I'll come to that in a slide.
You're going to try all permutations of system calls?
Yes. So, let's say, how do we deal with first single system call? We have read system call, let's say, which has a file descriptor, a buffer, and a size. We run this particular simple application, which reads something from the disk, and we get this kind of power profile. File read call starts, file read call ends. First step we do is we digitize it. We say you are in base state when nothing is happening on the SD card. You did something, you go to a high power state called D1. You stay there for as long as you're doing the work, which is described by the parameter of the system call. You come back to a D2 state, a tail state, and then you go back to base state. And basically just convert this into a finite state machine representation, which is saying exactly the same thing. You are in base state B, file read triggers you there, you stay as long as you're doing the work, you come back to disk tail, you stay there for a certain timeout, and you go to base state. To answer your question, Jitu, now, here, we'll try to do read calls from different states. Just the read call. We'll try to do, what happens if you do another read call when you're in high disk state? What happens when you do another read call when you're in tail state? So you're getting one finite state machine for one system call completely. Yeah.
I mean, it seems like there's still dependencies, though. Like what else is running on the phone? I'm just wondering how complete is this approach in practice?
So when we're doing this experiment, nothing else, we make sure minimal things are running so that the phone OS is working. Let's say, no app. Only app is running. But there could be interferences here. For example, you see some things going on top here from different components, but you need to average things out around these. We are controlling the phone entirely when we are building this model, so it's in our hands.
So, sorry, how do you know the firmware is not doing something? But how do you know? You said you're controlling the phone.
Right.
The firmware might actually be doing something with the hardware under you. You have no control. You don't have no visibility.
Right. So we assume the firmware or the device drivers do two things. They manage power based on timeout. They manage power based on workload. These are the two things where power state change they manipulate. However, a firmware could be doing something like if it is raining outside, I'll change the power. I'm not looking for it. It's a black box reverse engineering, so I won't capture that. Or a complicated power management. I'm not looking for that. I won't capture it. It's a black box reverse engineering. Yes, you do.
So I guess, forget about raining outside. In Seattle, that would be pretty easy. So suppose you had I can imagine a file system drive that would do something like, look at the percent fraction of reads and writes in some past period of time and change its cache management strategy which could impact power saving.
Sure.
So that's what I was asking. Do you look at a past history of system calls or just focus on multiple reads in a sequence, or have you looked at all possible? You obviously can't look at all possible sequences of reads and writes. So.
Okay, so one thing you're alluding to is what happens when caching is there and things like that. Okay, we'll handle that separately. But low-level things like a device driver could do hold of the read, do it later, or do some other things. No, we are not getting any information out of it. We are not capturing it. We don't observe it in phones. If we observe it in phones, this won't work. Yeah.
you seem to ignore the power drawn by the phone saying, I'm here, I'm here, I'm here, which dumb phones also do. Is that small enough to be negligible?
I don't understand. What do you mean by I'm here?
A cell phone keeps telling the tower where it is.
Right.
That also eats power.
Right. So that goes into 3G energy consumption.
What?
The 3G energy consumption, the radio energy consumption. So if you're modeling for radio, you need to capture that. If you're modeling for screen, you need to capture what is going on to the screen. If you're modeling for Wi-Fi, you have to capture what is going on in the Wi-Fi. One small point here, when there are workload-based changes, like 50 packets per second and so on, what we do is basically we change the size of the system call exponentially to see if we are observing any different power characteristics than this simple model. And we build the power model accordingly. Yeah?
I'm still a bit confused on how you capture path dependence, because what if you get a different Markov model if your experiment uses, let's say, 2 consecutive reads, let's say spaced by 10 milliseconds or something like that?
Okay, so the thing is, are the reads interfering or are the reads not interfering? Let's say they're not interfering. So basically what you're saying, when you're in high disk state or when you're in disk tail, what happens when a read comes in? Well, you just, you model it. You take the phone in that state, you do a read call, and then you model whether it's pretty simple, it goes to a high disk state and stays there. What happens when there are multiple system calls which are overlapping, going to the same hardware? Then you need to see in which order they have started and which order they have ended. We don't have that information. Reverse drivers don't get it out. What we simply do is we combine the workload of those 2 read calls at the time when they are executing, and we just stay in a high power state for that long. Second step, modeling multiple system calls going to the same component. Observation here is these kind of power management works at a very, very low level in device drivers. We don't expect there to be a huge number of thousands or something like states there, because programming at that low level is very hard. What we have seen in most of the devices, there are very, very few states, 3, 4, 5. And the idea is if there are very few states, you'll see these states being repeated across system calls, the finite state machines of different system calls. And the idea is sit down, you need a human, and identify which are the common power states. How do we do it? Wi-Fi NIC on HTC touch phone. Send system call finite state machine looks like that. You are in base state. You send at the rate of less than 30 packets per second, you go to low network state, cross the threshold, you go to high network state, come to network tail, a timeout of 12 seconds, you go back to base state. Socket close call on the same phone will take you from tail state to base state. You need a human to sit down there and identify that this 110 milliamperes in network tail and socket close call is same as 110 milliamperes in your send system call, basically, and then sit down and combine it. If you're in network tail state, either you have a socket close or a timeout, whichever happens first, you go back to base state. And you try combining different states for different system calls going back to the same component.
Why do you care about the combination?
Because when you're running an actual system, it may happen, your send call sends you into one state and now there is another system call. Now that system call won't start from the base state because your component is in a different power state right now. And you need to know what happens if that call comes in that power state.
Let me ask you, maybe difficult. So why don't you just simply combine all states with the same power?
You're doing similar you're doing similar things.
So why draw on the human here?
Sorry?
Why do you need the human?
You need to know which power states are same actually.
Can't you just do that based on the current drawn?
In all the experiments we did, yes, but it can happen that 2 power states have the same value. So you need to start sitting there and seeing what are the transitions that are coming into this state, what are the transitions that are going out of this state. Using that information, you realize whether they are the same power states or not. But yes, using everything that we have seen, a power value we can decide based on that. Yeah.
So do you have one big finite state machine that represents all, like the exponential combination of all states of all power components?
Right. So in most of the hardware, in Android, let's say, different components don't interact in terms of power. So you build one finite state machine for every hardware. For example, this finite state machine is for Wi-Fi NIC.
So you don't have one big finite state machine?
In Windows Mobile, yes, you do, because things start interacting, and now you can't just work with a single finite state machine of one hardware. I'm skipping that from the talk here.
So are you manually, there are hundreds, thousands, maybe tens of thousands of system calls, depending on how well you go.
Right.
So I'm wondering, are you manually mapping each, what you actually observe is that when you make a system call, the power utilization goes up.
Right.
But there's this extra variable there of which component is consuming the power. In this case, you're assuming it's network.
Right.
But in the case of the file system calls,
It's going to file. Right.
So what does that matter?
So for every hardware, you get what are the system calls that goes to this hardware. For example, for SD card, it goes file open, file create, file seek, file read, and so on. You build a finite state machine for every system call. Most of the system calls don't alter power state. File seek, it doesn't alter any power state of the SD card. So first state is you filter all the system calls that are capable of manipulating the power state.
And that you're doing manually?
Yeah, it's manual. It's manual right now. It's not automated. And then you start combining things.
So are there no system calls that ever affect more than one component?
We didn't observe this, but if hardware are interacting in terms of power, then implicitly yes. But the question is, how many system calls impact hardware? In our experience, not more than 5, 6, depending on what hardware you're using. So it's still a small space, you can do things manually. And moreover, power modeling is a one-time effort. It's all right, I spend some time. Once I have the model, I can distribute it to everybody. I don't need to redo it again until the hardware changes or the device driver changes.
Getting to Stefan's point from before, right, that the firmware controls a lot, even for the SD card.
Right.
Or for any flash-based system, the FTL plays an important role. When are the erasers happening? The erase consumes much more power than just a write.
Right.
So that kind of stuff. And if the firmware changes, you need to redo the model.
Right. So if the device driver changes, it is possible that power model changes, because you can go ahead and fix it, and there's no way around it right now. You have to actually go ahead and do this thing. We think this as you're writing a device driver. For every OS, you need to write a device driver, and then you need to build a power model. Yeah.
Can you handle things that don't involve system calls that can cause power, like writing to a memory mapped file?
That thing. Again, I said, yeah. Most of the applications use system calls as a primary interface to access OS, but there are ways around it. You can do IOPTLs, you can do mmap, you can do things like that. Right now, we don't cover it, but we can extend it properly.
What about when system calls have a delayed effect? You write something, you do a write, but eventually a worker thread decides to batch up 30 seconds worth of
caching. Any cache layer. There are several cache layers. There's caching at GPS, they're caching at SD card, they're caching at network and things like that. The general idea is you need to log everything above the cache and everything below the cache, so that you know when is the hardware getting triggered, when is the request coming in. We did it for GPS in Android, because it's easy to go at the framework level and do this kind of stuff. Low level device driver is doing, no, right now it's out of hand. It's because we don't have this information. But the framework remains the same. The theoretical assumption is like you need to log above, you need to log below. We implemented this on 2 OSes, Windows Mobile 6.5 using CElog, and Android using System Tap. We logged kernel events. I'm not going into details of this. There's a huge amount of engineering involved here to make sure the overhead is very less when the applications are running, so that they don't reduce a lot of energy drain because of logging framework. The results, how do they look like? We run a different application on Android, Windows Mobile 6, YouTube, Facebook, Maps, Chase, virus scan, document converter, different things. And we use the finite state machine model, the RS one, and the linear regression based model, the state of art. We plot the y-axis as the error percentage. We run the application for 10, 15, 20 seconds. We see how much energy is being predicted, consumed by our model, how much energy is actually drained by the power, using a power meter, and we plot the error bars. We see finite state based machine model is under 4% of error, and linear regression models are 1 to 20% of error. But not only that, when we see what happens at fine-grained intervals, instead of measuring energy for like 20 seconds, look at every 1 second, how is the prediction? We found that even that is really good. At 50 milliseconds bin, 80% of the 50 millisecond bin has less than 10% errors in our model.
Question. The impact of the screen is going to diminish your error percentage because it's such a large and constant factor.
Absolutely.
what happens when you look at these numbers taking out the screen constant?
Of course, they'll increase, first thing. So in this kind of graph, we have taken the screen value to be absolutely lowest brightness. But the problem with doing that is when you remove the screen off, and at some point you're predicting some energy consumption when the phone is not actually consuming any energy, you're getting infinite error, basically. So there are periods where the model, very fine-grained period, let's say 50 milliseconds, if you're looking at that time interval, there are periods where a model returns 100% error sometimes. That is true. But overall, we are pretty good. Most of the 50 millisecond bins, we are very low error. G2 is in the pipeline, sorry. Yeah?
Actually, I also have a question about the screen. Just as a point of information, what fraction of power in each of these cases was roughly going to the screen?
It depends on what brightness you have set, what hardware you have.
Okay, so you said lowest brightness. So for example,
right,
most of the time 50% of the power was going to the screen, 20%, 10%?
It ranges from 25% to 75%.
25 to 75%?
25 to 75%. Yeah, okay. And if out-of-box phones, it's 35%. The screen, the brightness value, which is set. Again, it depends on hardware, whether the screen is OLED or whether the screen is LCD. LCD screens is what I'm quoting. OLED screens are even less because it depends on what color the pixels is and things like that. So that number goes down.
Sorry, one quick follow-up question. Is this error systemic in the sense that is your model, for example, always over-predicting while linear regression is always under-predicting or something?
No, it's all over the space. It's all over the space. Sometimes we are over-predicting, linear regression is under-predicting, and things like that. Yeah.
So you've described this system with finite state machines that you spent a lot of time optimizing and getting right. You described the problem with linear regression. You described 4 of them, any of which one might correct. For example, one might try nonlinear parameters. How do I know that you wouldn't, if you had spent the same amount of time trying to get a regression model right, that you wouldn't do better than you did here, given the number of things that a researcher who was interested in seeing the regression model succeed might have done to better optimize a regression model?
Right. So there are multiple ways you can optimize regression model. You can build a different model in finite state machine and so on. And what we say, once we build this model, we observe that the most important property of our model is not the accuracy. It is something else. I'll go to the next slide. It is you're tracking it back to the application, and now you can do energy accounting. But yes, you can make linear regression better. That's, of course, that's maybe possible. We have not done that. But if you're working on performance counters, it's very hard to answer the question, which thread, which routine is consuming how much energy.
It's just to have more error.
You need
on Android, you get per application usage of resources, and you can easily build a linear regression.
If you get those kind of numbers, that's good. Which routine is consuming how much CPU, which routine is consuming how much disk, how much network. If you get that kind of. At application layer, you get those numbers. But we started from the fact that which routine, which thread, we want that kind of information.
As a scientist, I'm still really bothered here because we've got, you're doing a test that's combining, that's comparing 2 things. But one of the things that's different about these 2 models is that one's finite state based, one's a regression model.
Right.
Another thing that's different is you're using different independent variables. In one, you're using performance counters, as you said, and in one, you're using syscalls.
Right.
And you could have built the finite state machine, or you could have built the linear regression based on where every one of the independent variables in your linear regression is the number of times a system call was called.
No, we're not challenging that cannot be done. That can be done. First thing, you can extend linear regression-based models. You can make them more accurate. But the problem is, until and unless you don't remove those assumptions from those models, you cannot get them right. The assumption is only active utilization. We are targeting that. Energy scales linearly. If you remove those assumptions, then probably you can do a better job. Irrespective of what mathematical model you use, is it linear regression, better of it, finite state machine, and so on. Yes?
So, a question, just as a Seattle resident, not as a scientist. To restate the scientist question, there are 2 things you changed. One is you went from instrumenting performance counters to system calls.
Right.
One is you went from
linear regression model
to a finite state model. In your intuition, which of those is the key insight? Is one of them key and the other one irrelevant, or?
So there are two things. One is accuracy, how good you are in terms of prediction, and what we know from the power behavior that there is actually finite state based machine power model in device drivers. Something happens, you change the power. Something happens, you bring back the power. So we are good at capturing that. The second important thing is, next slide, a couple of slides. How do we track it back to application? Yes.
So if I understand you're saying the finite state machine is the important part.
Finite state machine is the important part, but equally important is the second half. It's based on system calls. Yeah.
I just wanted to get a sense of the size of the finite state machine built.
We observed 4 or 5 states in most of the hardware, a few transitions. That's the size for each of most of the hardware components. Yeah.
One other question. Do you know why linear regression is doing better in the game and the IE scanner scenarios?
Game is mostly CPU. CPU consumes nearly linear energy if you're running at a highest frequency. That is why it's performing roughly better when you're looking end-to-end energy consumption. I've removed a graph where it says what happens in individual prediction. There, in some places it is overestimating, in some places it is underestimating, so when you're looking end-to-end, you're getting really good result. They're canceling each other out. Okay. So, we started with this question. Where is energy spent inside my application? We did the power model. Second thing is we need to track application activity, and the granularity of tracking depends on what is your requirement. Do you want per routine, per thread, maybe a combination routine, and so on? We say, let's try to do per routine because that's the modular programming language. We use gprof-like mechanisms to predict how much CPU energy is being spent in different routines when they are running on CPU, because it's very hard to profile. It's very high overhead to profile when a routine starts, when a routine ends. We use sampling, PLDI-82 paper straight out of it. The third thing is you need to map power activity to app activity, and we use the most important part of this finite state based machine model, that is it's based on system call. And now you can track system call all the way to where they're coming from. Get PID, which process is doing it. Get TID, which thread is doing it. Backtrace, which stack of routine is doing it. And now you can do energy accounting. But then there is one problem of lingering energy consumption, and we need an accounting policy for this. So what is lingering energy consumption? The first case is very simple. The tail energies. Let's say a routine foo sends 10 kilobytes of data. The send is done. But then, even then, 3G consumes a high tail energy for up to 7 seconds. This foo is the cause of this tail energy. But even after foo is completed, the thread is completed, the process is completed, the hardware lingers on and consumes more energy. You need to take care when you're accounting the energy back to different entities. The second case of lingering energy consumption comes from something called persistent state wake locks, and now we are going to the next half of the talk. What are these wake locks? Smartphones have a very, very aggressive sleeping policies. The moment you stop interacting with the phone, within few seconds, the screen shuts down, the CPU shuts down, the system is frozen, and that is why your phone lasts a day in your pocket. This has a lot of problem for programmers because your program may be in the middle of doing something very important, like it's talking to the server, and the CPU sleeps. Now the server says, where is the phone gone? So the smartphone OSes give developers some APIs using which they can keep components on explicitly even though the user is not interacting. For example, you're talking on Skype. You need the screen to be on. You don't want to touch your phone every 5 seconds. The screen needs to be on from the call started, and the screen needs to go off when the call is ended. The thing is, let's say a foo routine says, keep the screen on. It acquires a wake lock for the screen. And the foo is over, but the screen continues to consume energy even though foo is over. It's consuming energy on behalf of foo. And this is another example of lingering energy consumption. So let's say, how do we deal with lingering energy consumption? This is an accounting question. I do a send. Send takes 10 kilobytes. There is a tail. We split the energy into utilization-based energy and tail-based energy. And the first thing we say is, these two energies are different, U and T. Let's represent energy as a tuple rather than U plus T. And in this particular simple example, it's very, very easy to observe that U comma T tuple should be assigned or accounted completely to this send system call and whoever is calling this send system call. Nobody else is responsible for it. What happens when there are multiple system calls? I do a send 1, I come into tail, but before the tail is over, a send 2 comes in, or receive comes in. There is a utilization energy, there's a tail energy, there's a utilization energy and tail energy. First thing, the first tail T1 belongs to send 1 because send 1 started that tail. Now the question is, how do you split T2 among these two system calls? There are several policies. There's nothing right and wrong here. Let's explore the policy space. First is the average policy. Split tail energy T2 in some weighted ratio among send 1 and send 2. But the problem with this is it's not always easy to define weights. For example, instead of send 1, let's say it's a file open system call, and send 2, it's a file read system call. How do you define weight for file open? It could be a connect system call, it could be a send system call. And the problem is the policy gets complicated if there are a huge amount of system calls and you need to wait until all of them are over and then you start dividing them. We take a very simple approach. We call it as the last trigger policy. We say forget about everything else. We are representing energy differently. Allocate T2 completely to the last guy who called it. Send 2. And go on. We don't need to define weights. We don't need to, the policy is not complicated. Yeah.
Punish the guy. The guy who goes first is responsible for taking you to a state where you're going to have the phone on for a while. The guy who goes second, if he times it right, he's just being opportunistic.
Right.
So the only additional cost really incurred if I as an application decide, hey, someone else has activated the phone, I should take advantage of this, is the difference in time between when my call ends and when the previous guy ends. Because that's the additional time that has to wait because so if you take a last trigger policy, then you aren't giving any reward to applications that time their events opportunistically to minimize power. They're always actually being punished. They're incentivized to actually waste power in the last trigger policy.
This is an accounting policy, first thing. There's nothing right, nothing wrong. It is which gives more information to the developer to debug their application energy consumption.
By that token, Stuart's argument is right. I think, yes, it's a policy, but some policies have incentives.
Right. Policies are incentives. You can. This is again not a runtime system. You're doing at the end of it. You're collecting the trace. You're predicting energy. What we realize is, at the end of the day, whichever policy you use, you come up with a flat energy representation. How much routine X consumes energy, how much routine Y consumes energy. And this is very limited in terms of information, irrespective of what policy you choose when you go on debug the application. We come up with a new way of representation, which we call bundles, which actually take this question completely off the table. We are not accounting tail energy at all, but we are representing the energy consumption to the developer in such a way that he can quickly understand what is wrong in the application, what he's doing wrong, and he can optimize that. Because that's our main goal.
I don't think there's any way to piggyback intelligently at this point. So I think I think that's an important feature you could add to a system is to say, I want to just, if someone else is sending, I want to send then.
Right.
But I don't think currently in the operating system, as far as I know, you can't do that. If you could, that might be a problem, but right now nobody can program against that API. So the incentive is to add that API, right?
So once you have such kind of API, you can do much more things. Then you get the incentive, and then you can notify application what is the opportune moment of doing things. But that is a completely...
Then you could actually have a system where you batch everything intelligently. And if you just want to be an opportunistic app, then you could get a lot of benefit from doing that.
I'll bring it up at the end of the talk. I actually disagree with that.
It is visual. It's going to be in the chart.
Yeah, there isn't. So you can't.
You can enforce.
Right.
You can't do it yet.
So we implemented the cprop. The implementation looks very simple. You do code instrumentation logging. You run the application. You have the application. You embed energy APIs into it to start the tracing, stop the tracing, install it on a mobile OS where you have system call tracing enabled. You run the application, gather a trace, run it on a server to get in-depth energy profile. give the data presentation, the bundle presentation that I'm talking about. It's not in the slides, but we can talk about it. The runtime overhead of this system was 2 to 15%, and the run energy overhead of the system was 1 to 13% additional energy incurred by tracing. We use this on several popular applications like Angry Birds browser, Facebook, New York Times, and we had several insights of where energy is being spent. The first is free apps drain a lot of energy doing everything you don't need. I'll come back to in the next slide. A major finding is I/O consumes a lot of energy on phone. CPU is not the bottleneck in terms of energy. CPU consumes less than 10%, 15% of energy. And what we'll show here is eProf helps detecting something called no-sleep bugs. First sample case study, Angry Birds. One simple game, 30-35 seconds, shoot three bugs, birds. We found that the user tracking where you are, uploading this information consumed 45% of energy. Fetching advertisement consumed another 28% of energy. The core gameplay, the physics engine, the rendering engine consumed only 20% of energy.
But you're not even displaying. Are you displaying on GPU?
GPU is not there on Android yet, before Ice Cream Sandwich. Screen is allocated, the accounting is done based on wake locks. It is accounted to who is holding the screen wake lock, which is basically the Android framework process. So Angry Birds doesn't get any share of energy. But somehow if we are supposed to put that energy down into here, these numbers go down. Instead of 75% of energy going into advertisement, it goes like 40% energy or 45% energy goes into advertisements. Now this was picked up by Popular Press very recently, and there's a nice story around it, how press gets very aggressive. They first said people tested Angry Birds and they found a lot of energy is going, 75% energy is going in free applications. Next round of press releases, all free applications drain 75% of energy in advertisements. Next round, Abhinav Pathak says you should buy paid applications. We never tested paid application. Next round, this study is from Microsoft. They are trying to show Android is bad. You have a question?
There's a big gap here between, you're showing activities as a very high level of application. The system calls it very low level. So
Right. Right, we have an in-depth, a huge profile for this, thousands of routines. And then this is basically clustering based on which threads. There's a Flurry thread that comes with Android, which does all this tracking, getting advertisements. So we have aggregated those numbers. Second example, we found something called a Wakelock bug in Facebook application. I run the Facebook application, and I observe something called a Facebook service is consuming 25% of energy. What is this Facebook service? The Facebook service basically polls the background to see notifications. Somebody sent you a friend request, somebody wrote on your wall. And this was surprising 25% of energy because during the time of experiment, nobody wrote on my wall. Nobody added me as a friend request. I'm not that popular anyway. What we found out of this 25%, roughly 20% was going into something called an acquire wake lock routine in app session class. What it was basically doing, it was telling the CPU, please keep the CPU up. I'm doing something very important. And it never ever told the CPU or the OS, the CPU is free to sleep. And all the energy of the CPU low idle state is accounted to this guy. This is an energy bug, very popular in Facebook application. We switch gears now. We built an energy profiler, which is a semi-automatic approach. We go to an automated approach of finding no sleep bugs, one of the most notorious kinds of energy bugs. We will show a compiler-based approach. What is no sleep bugs? Why are they coming? What is this new problem here? There's a philosophical shift in power management when you move from desktops to mobile. Everybody here has written programs in Java, in C, C++, some language. How often in your application source code you needed to take care that the CPU is on? How often you needed to take care screen is on or any component is on? Never. But when you move, this is because there's the default power management philosophy, the default thinking is everything is on, it's already there for you. You move to smartphones, there's a different power philosophy. Everything is off by default. And if you want something to be on, you need to explicitly ask for it. Smartphone OSes aggressively turn things off, but they provide a lot of APIs. What are these APIs? How do they look like? Let's say I'm doing some network, trying to sync my emails over network. This may take a minute or so, over 3G maybe, let's say. If in middle CPU sleeps, I'll have a problem, because now the server thinks, where is the mobile gone? What does the developer do? It acquires something called a wake lock. Says to the OS, please keep the CPU on. I'm doing something very important. I'm done doing important. I'll release the wake lock. And now you're free to sleep as per whatever you want. Example from Skype. You need to keep the screen on. These are 2 example APIs from Android. There are 7, 8 of them for different components. But what this leads to a new phenomena which we call as power encumbered programming. You are pushing all this management of sleep and wake cycle all the way up to developers. And some of these developers could be high school kids trying to earn a quick buck, or even the most professional programmers do a huge number of mistakes when they're using these APIs. This results in something called a no-sleep bug, which is basically an application telling a component, please stay on. I'm doing something very important. And it doesn't tell the OS that I'm done doing important. You can shut it down. If that component is CPU, 50 to 60% of battery goes in 12 hours without you using the phone. If it is screen, 100% goes in 4 to 6 hours. If it is GPS, 100% goes in 3 to 5 hours. We have examples of all these category, including popular applications like Google Maps, SMS application, Facebook was CPU category, and so on and so forth. So we started looking at these no-sleep bugs, and we said, why programmers are making this kind of errors? What is the problem they're facing? And we categorized no-sleep bugs into 4 categories. One is no-sleep code paths, no-sleep race conditions, dilations, sleep conflict. I'll go through 3 of them here in this talk. No-sleep code path. The programmer actually said in his application, keep the CPU up. And somewhere he said, the CPU is free to sleep, but the code took a different path than what the programmer anticipated. I'll give you an example. Let's go back to our do network example. You're trying to sync over network. You acquire and release the wake lock, but let me throw some Java into it. Your sync over network throws exception. Something bad happened in the program. You try to open a file, it's not opened, you divide it by 0 and things like that. And the programmer just did try and catch across this block. When there is an error exception, you just print the information, what is the error, debug it later, and go ahead. What happens? You have introduced a no-sleep bug right there. You come here inside, you tell the CPU, don't go to sleep. You start syncing over network. You catch the error, you print the error, you go on. Who tells the CPU that it is free to sleep back again? Question?
When did 4 bugs go away if the wake lock had a timeout in it?
That's a good question, and that's one of the questions we are looking at. Some of wake locks have timeout in them, but this is a question we are looking from how do you improve the programming languages or API to provide better solutions. But the problem is, let's say, even though I have a timeout, I acquire a wake lock for 60 seconds, let's say, and then at the end of 60 seconds, I still want it to be on. So I put this wake lock acquire 60 seconds in a while loop, and I make a bug there. The problem still remains, but yeah, some of it can be taken off with a better use of programming constructor, a better API. Yes?
The conventional way to solve this in OOA is to replace the 2 calls with an object that has a destructor that goes out when it goes out of scope.
A destructor is not always guaranteed to be called. We have a very nice code snippet coming from Android where the developer is absolutely confused what is going on. He put it in finalize, and he wrote a comment across it saying, I'm not sure if this finalize will get called because Java doesn't guarantee the finalize to be called. But it can happen, some code doesn't release the wake lock, and I don't know what path it is, and let me just try it. But it's not guaranteed again.
It's been a while since Java for me, so
yeah. But the problem is still, again, most of the smartphone applications, they don't get killed. They stay in the background. So if the application is on, the garbage collector won't get kicked in. Well, if the wake lock is acquired.
I was thinking C++ style scoping, so it would have taken care of this.
That's one of the ways you can solve this problem, maybe. We observed this bug in several applications, Facebook, Google Calendar, the dialer app, which I started with. No sleep race conditions, very similar. Let's say a process have 2 threads, thread 1, thread 2. The wiggly shows the execution path and the timeline goes down. The red dot shows that thread 1 acquires a wake lock. It tells a component, please stay up. The green dot shows thread 2 says that particular component, you're free to sleep. And everything goes right, it's all good. But let's say the threads are organized differently. Thread 2 comes up, says component is you can sleep. That's a no-op basically right now. And thread 1 comes up and says, please stay up. And nobody else after that comes up and says the component is free to sleep. The default Android client has this bug. Still now it's not fixed. I'm going to sleep conflicts directly. And this is very interesting problem. Let's say I'm doing something on the phone and the power profile looks like this, the timeline and the power consumed. What I did was basically I started a Wi-Fi transfer. My Wi-Fi transfer is done. Wi-Fi goes into a network tail. And at the end of 2 seconds, the device driver kicks in, says 2 seconds have gone, nobody has done any communication, put the phone to sleep, put the NIC in a low power state. So far so good. What happens when sleep conflict strikes you? You start the network transfer, your network transfer is done, but when you are in tail state, let's say the CPU sleeps aggressively. The problem is now the code piece that will run on behalf of device driver that will tell the NIC to go back to a low power state cannot run because CPU is sleeping. Your NIC keeps your phone warm in your pocket. We have a very nice video where we show 2 lines of Android code can induce a sleep conflict in a vibrator. We ask the vibrator to run for 10 seconds, but it continues to run for 10 minutes. And this kind of bugs are present in GPS, NIC, different hardware components. Tracking and debugging all these energy bugs is a very big problem, very hard problem, and it requires synergy from different parts of computer science like architecture, programming languages, verification, and so on. We'll show how we use compilers. One of the very simple technique from compilers to solve no sleep code paths and no sleep race conditions. We use this solution from Compiler 101 book that comes right off the grad course. It's called Reaching Definition Data Flow Problem. And the problem statement is pretty simple. At every point in the program, statically tell what are the definitions of different variables reachable here. And you can do a lot of things using this information. For example, let's say at this point, if y is greater than 5, you know what are the values of y reachable here. In this example, it's just y is equal to 11. So you can remove the if branch completely. You can remove the else part. You just put the if part because always if will be true. You can do a lot of optimizations around this reaching definition data flow. Well, how do you do it? I'm not going into detail of it. You build a control flow graph of the application. You compute some gen set, skill sets. It's compiler 101, very simple. At the end of it, you get at every block, what are the definitions reachable? For example, here we say D2 can reach the exit block. D3 can reach the exit block, but not D1. We'll use this straightforward. We'll try to find out no sleep bugs due to code paths. We have Wakelock acquire, we have Wakelock releases. What we do is we build a control flow graph, which looks like this. I acquire a Wakelock. If there is an exception, I go to catch. Otherwise, I release the Wakelock. I come to exit. I transform this simply saying, whenever you switch on a component, I'll turn that value to 1. Whenever you switch off the component, I turn that value to 0. And I apply reaching definitions problem straight away here. I'll say, at the exit node, I get 2 definitions reachable, D0 and D1. D0 is good because the value of 0, Wakelock is coming in, which says that the component was shut down. This is a good value. D1 is good. D0 is a problematic because it's coming from an exception path. It's saying the Wakelock value is 1. You're reaching the end of the code path, but still it is holding the Wakelock. As simple as it sounds, it's there's a lot of complication here coming out of event-based Android applications. All the applications are event-based. Your applications no longer have a simple main, and the call graph is very hard to build there. We handle those kinds of stuff. We handle Java runtime issues of what happens when issues comes, runtime exceptions and things like that. We handle special code paths. This is a static technique. We are trying to be conservative. The moment you try to be conservative, a huge number of false positives kick in. We apply a lot of cases to reduce the false positives. We implemented this in Suit. This is a Java pre-compiler. We tested on 500 market applications, random applications. We found 48 applications which had bugs. Most of the problem was incorrect event handling. The developers did not realize, they do not understand how Android event-based model works, how call transfer from one place to other. The second category was if-else or exceptions, just like the Facebook bug. In 6 places, the developer forgot to release. He just acquired it, and there's no release throughout the code. And there were a few miscellaneous categories. To conclude, in this talk, I've talked about eProf, the first energy profiler for smartphones, which gives in-depth information of where energy is going inside your application, which routine, which thread, which process is consuming how much energy. It's built on a power model, which is a very fine-grained, accurate power model. This is, again, a semi-automatic approach, and we can build automated approach to track energy bugs. We showed one example from compilers. Future work, you can use different areas and solve more energy bugs in an automated way. You don't need the developer here. But just to put things into picture, we are still looking at a very, very small slice of the problem. You need to track energy bugs in framework, in kernel, in firmware, in hardware. It's part of network. And that's the future work that we propose. I'll have just a couple of slides to talk about what is the other work I've done during my PhD life. One of the work falls in the spam category. There was a point in life we were tracking a multi-million node botnet spewing billions of spams every day. And we were able to characterize some of the features of how the botnet works and so on. Using the data, we showed that the state-of-art spam detections, spam campaign detection does not work. It has a huge number of false positives when it comes to tracking botnet spam. And we built a first complete unsupervised spam detection system, which removes completely human from the spam detection loop. The second case, the second set of work is data center and internet measurement. We worked for some time with Bing team to reduce latency between data centers and client, and we were measuring something in routing and internet. I'll be happy to talk about them in one-on-one meetings. And with this, I conclude my talk. Thank you.
Earlier, when you were talking about accounting policies, you said it doesn't really matter. You can imagine any accounting policy is fine, but it seems like an accounting policy is better than another if it leads developers to better understand their bugs.
Right.
Did you find that when you tried one accounting policy versus another, developers in studies would fail to find their bugs or get misled?
Right. So if you're looking for energy bugs, then you need to allocate energy about who is responsible for this kind of stuff. But if you're looking for optimization, for example, in Angry Birds is consuming 75% of energy in advertisement. How do I cut it down? If you're trying to look for those kind of information, then yes, policy is important. And we spend a lot of time around this, that what is the best policy? At the end of the day, we realize irrespective of what policy you use, as long as you're using a flat representation of energy, it's not that informative. That is.
So it didn't matter to user studies.
Right.
Developers were just as effective.
Right. And that is why we moved away from flat representation of energy to something called bundles of energy, which is tackling specifically why is I/O draining so much energy. I've not covered this in the talk, but I can talk about it.
Suppose you had, like, I think following behavior and like, suppose you told the user for every app with correct accounting how much energy it used. What impact do you think that will have on users and developers?
So there are a lot of tools currently available running on smartphone systems that tells user how much energy is being consumed. And there are a lot of problems with those tools as well. But then the immediate impact we see is now users have something in their hand and they can complain about. You see, I used my smartphone and this says Facebook is consuming a lot of energy. And now a lot of pressure is there on Facebook. Well, developers might want to handle it, developers don't want to handle it, but then online there is a lot of pressure on them. But the set of tools that we are developing, they are mostly targeted towards developers. Because they don't have right now a tool that can help them debugging. You require tools at every layer, not only for users, but for developers, for kernel people, framework people, and so on and so forth, because at every level you require energy cut down.
Okay, let's thank the